Okay, I found this paper which has some nice figures showing the differences between the responses of the Arctic versus the Antarctic to climate change, basically increased greenhouse gases and other forcings that we humans are creating. Uh, you can easily see that even in the long term 1901 to 2023 warming trend, you can see that the warming over the longer term is of course milder, and yet you can see despite all the data gaps and data non-uniformity, let's say, over time, you can see that the Arctic has warmed faster, and then there are drier regions like the Mediterranean and the uh, Middle East that you can see has warmed faster as well. The Atlantic here, it's been talked about a lot, but you can clearly see the difference between this is for 1994 to 2023 to show that the warming rates have greatly accelerated more recently, and you can see clearly the so-called polar amplification, the Arctic amplification, which is not so clear here, and there are many more data gaps here than here, but despite all that we can say confidently that the response to increased greenhouse gases is quite different. And in the Antarctic versus the Arctic, you already probably have an intuitive sense that since the Antarctic is encircled by the Southern Ocean, which obviously is warming up and can create complicated things like melting the glaciers, ice shelves from below, but creating more water vapor in the atmosphere and creating more snow in some places. So the trends in the glacier growth and loss are not uniform over the Antarctic. So it's a bit more complicated than this. In that context, this is the paper. Why does Arctic sea ice respond more evidently than Antarctic sea ice to climate change? Okay, so we'll see a figure that will show clearly that the Arctic is almost like a semi-enclosed sea, and because of all the runoff from the land, it's fairly fresh, almost like a lake. So you get fairly thick sea ice here, whereas the Antarctic is wide open, and if you know anything about sea ice dynamics, you cannot grow sea ice to be very thick in the open ocean, because as you keep releasing the heat and freeze the water, it releases brine, the salt is ejected, which makes the density higher, so the water tends to sink away, and then you set up a circulation, which means you are bringing newer and warmer water, relatively speaking. So the sea ice, although once sea ice is formed, it can insulate and prevent the heat loss, but it can also keep getting this new heat. So keeping all those things in mind, the Arctic sea ice in general is much thicker than the Antarctic sea ice anyways. We'll see some data on that. So this is from a journal called Ocean Atmosphere Land Research, which is published by the AAAS in the US and some lab in China. The current climate change episode has impacted sea ice in the two polar regions differently. In the Arctic, remarkable sea ice extent and thickness declines have been observed, with a stunning depletion rate of old ice. So there is an ice age that we'll talk about. No similar changes have been observed in the Antarctic. In this paper, the question posed in the title is addressed by reviewing findings retrieved from previous publications. So it's a meta-analysis. The paper starts by identifying key geographic and climatic features and sea ice characteristics in the two polar regions and summarizing relevant recent records. It then proceeds by investigating the interactions between sea ice and the environmental factors, including atmospheric, oceanic, and dynamic aspects in each region, as well as the increasing number of icebergs in the Antarctic. It's concluded that the peculiarities of each polar region renders the response to climate change differently. Researchers should not apply scenarios regarding the impacts of climate change on the Arctic Sea, or that is the retreat, to the Antarctic sea ice. Instead of asking why Antarctic sea ice has not responded to climate change in the same way as the Arctic ice, a more reasonable question could be, why Arctic ice changes are yielding an annual cycle that resembles that of the Antarctic ice. Okay, so there is loss, but the loss itself has a annual cycle, obviously summer melting versus winter accumulation or winter loss and so on and so forth. And there is obviously an annual cycle in the Antarctic ice as well. And the loss, see, the annual cycle of the Arctic ice changes look similar to that of the Antarctic ice, even though the trend responses are very different. This could result in the Arctic sea ice becoming predominantly seasonal during winter, almost completely melting away during the summer, which is the current state of the Antarctic ice. Because Antarctic ice is in the open ocean, it tends to disappear and reappear on a seasonal cycle, whereas Arctic ice has a lot of old ice, multi-year ice, which is disappearing now and maybe become more seasonal. Obviously, if you build seasonally and melt away in the summer, you will not continue to accumulate in thickness and in extent the same way as seasonal ice, so keep that in mind. So here are the connections the Arctic has: flow out through the Canadian archipelago, the Fram Strait, and another branch of the Fram Strait here, and you have inflow from the Bering Seas here through the Bering Strait. So these things make a difference. This region is also fairly fresh compared to the North Atlantic because of the ocean dynamics that you may have heard about. I have podcasts on that in the oceanography course that you can look up. Whereas the Antarctic obviously has its Weddell Sea sector, Indian Ocean sector, Western Pacific sector, and Bellinghausen and Amundsen Sea sector and Ross Sea sector here. So this vast ocean water that is warming up and having contradictory effect, because warming ocean, as I said, can begin to melt the glaciers from below as they come out as ice shelves onto the ocean, and waves of course can break them off. Wind shifts affect the waves, and then the warmer atmosphere, moister atmosphere, can increase snowfall in some regions, and so on and so forth. So the story is complicated. The annual mean temperature anomalies of the combined land ocean for the global Arctic, so north of 64 north, and Antarctic south of 64 south, so slightly inside of the polar circles. Annual surface temperature, you can see Arctic has clearly warmed much faster more recently, and the Antarctic has remained almost flat, but the global warming is there, which is consistent more with the Antarctic warming. But Antarctic warming of course has large interannual variability. In the global mean trends, anomalies, you tend to wipe out a lot of the interannual variability because you are taking different signs of the changes and averaging them out. And this is the temperature anomaly with respect to the 1980 to 2015 baseline. This will also be with respect to some baseline which is typically 1961 to 1990 or 1850 to 1900 and so on and so forth. But the baselines don't matter, they just shift the relative magnitude of the anomalies. Monthly average anomalies of the surface air temperature over the Arctic region using MERA2 global reanalysis models. So reanalysis, if you don't know what they are, I have them elsewhere. You can look up on the podcasts, listen to podcasts. But basically, quickly, they are dynamic models that take gappy data in space and time and assimilate them and produce the best dynamically interpolated reconstruction of past climates. So we're taking each year here. You can clearly see going from 1880 to 2022, things have warmed up, and you can see that there is still interannual variability. So the decades of the 1980s to 2020 are all warmer than the one before, because even though there is interannual variability as we saw here, each decade is now warmer than the previous decade, and Arctic amplification makes it fairly clear. Okay, so what about the area of the sea ice in kilometers squared, millions of square kilometers? This is the Arctic, so you can see maximum sea ice extent in February, March, and there are some trend lines drawn here. You can see that this is here the disappearance of the September ice, minimum sea ice extent, is faster than the winter sea ice extent disappearing, obviously because of the amplification and the summer. So obviously you remember that the September ice extent is very critical because that can really determine how much more the ice can grow back during the fall and winter months. If it disappears by a lot, then you have a harder time rebuilding because of the ice albedo feedbacks. And on the other hand, Antarctic sea ice area in millions of square kilometers, you can see areas here seems on the mean larger for the maximum sea ice extent in the opposite sense, so August, September, and the minimum is much smaller than the Arctic because you have seasonal ice, as we said, but the main thing is you hardly see any trend at all over this long period, right? So obviously there is a bigger debate about when is a trend a trend. What if there is decadal variability during this period of 1975 to 2024? Well, we have to keep that in mind. But here you look at standardized anomaly of the average of 1980 to 2010, and they are basically showing anomalies of Arctic and Antarctic sea ice extents expressed in terms of the number of standard deviations from the average over the 1981 to 2010 period, as it says here. The three lines indicate the monthly anomalies and thick lines indicate 12-month running means. Gives you a better sense of the low frequency trends. Note the steep rate of Antarctic sea ice extent decline and the highly moderate rate of increase of the Antarctic sea ice extent. A sharp rise followed by a sharp decline is observed in the Antarctic data during the 2012-2017 period. So there are high multi-year timescale variabilities here as well. So Arctic, of course, is taking a nosedive despite the ups and downs of the interannual variability. There's some loud noise coming from outside. I want to make sure it's not coming from my apartment. But the Antarctic almost seemed to increase when averaged over the whole area south of 64 south, jumped up sharply and then took a nosedive here, and you can see various running means as well. So the running mean, 12-month running mean here shows a slight upward trend, and this shows a sharp downward trend. So this you have to be really careful. This is about ice thickness, just comparing January 2015 to January 2022. When you do such a close period and just 1 month, seasonality, interannual variability, etc. can be issues. Seasonality is not, of course, but you can see that 2014 was a warm year, 15-16 was a very strong El Nino. So January 2015 would have been just coming out of the warm period. Okay, so I'm getting a phone call. Let me stop here and we'll continue in the next podcast.